Well, hi everyone. My name is Oliveira, and I'd like to present an introduction to counterfactuals. I'll split this presentation into three main topics: the basic and general concepts of what is a counterfactual, what are the desirable properties of a counterfactual, and how we implemented a counterfactual search. So let's start with defining the very general concept of a counterfactual. Let's assume we have a predictive model we want to use. We don't know how this model was trained or which algorithm is calculating the prediction. It could be anything. The only thing we know about this model is what kind of data it takes as an input and what kind of data it returns. We usually call this model a black box model. Now let's assume that this model is being used to predict the outcome of a loan application. I provide it with the application's data, the input, and it will return the prediction, the outcome. Now let's say that for a certain application, the model predicts that it will be rejected. A counterfactual explanation will allow to query the model with an alternative question. Using counterfactuals, we can ask, how do I need to change my inputs in order to get my application approved? The model will be used to provide us this time not with an outcome, but with inputs as close as possible to the original ones, but which lead to the desired outcome. We can now provide then a very general definition of what is a counterfactual. We'll define it as the smallest change to the input features that change the prediction to a desired outcome. But this definition is still too general. Let's look at the desirable properties of a counterfactual into more detail. There is a large body of literature on explainable AI and counterfactuals, and it is an actively researched field. However, we will present three very fundamental properties and we'll look at them individually. These properties are validity, sparsity, and actionability. So let's start with validity. Validity means that a counterfactual has the minimum distance between its associated outcome and the desired outcome, but also between the counterfactual features and the original ones. If we think of the previous example, this means that the counterfactual should minimize the distance between its outcome and the application approved, and between my actual application data and the proposed data. But which distance? Distance has an exact meaning in this context. Let's assume a minimal model, simply for illustration. We provide an income and a score, and we either get approved or rejected. We mark our initial data, which the model rejected. And we can picture a decision boundary, that is, a line that marks the point at which certain combinations of inputs lead to approval. If we knew where this boundary was, things would be easier, but our premise is that we are dealing with black box models, where typically we don't know where that is. So we could try some methods, like using purely random combinations of inputs and trying to approximate the boundary. With this approach, we will just sample the feature space until we found some sufficiently close answer that will flip the outcome to the desired one. But this will be, of course, very inefficient. Additionally, if we have several counterfactual candidates, we need to apply the validity criteria. For a set of counterfactual candidates, we need to calculate the distance between the original point and the proposed features. For the features, we can use, for instance, a Manhattan distance, calculated feature-wise, and for the outcomes, an Euclidean distance can be used. However, different metrics can be used in specific problems. Once we've calculated the distance, we choose the best counterfactual as the one which minimizes the distance. And at this point, we can designate the result as a counterfactual, which can be formulated as a definition in the beginning, stating that if the input was this, then the outcome would have been approved. Formally, we can write validity in the following way, where the counterfactual should minimize the total distance between outcomes and inputs. We will now look at the sparsity property. Sparsity means that a counterfactual should change the minimum amount of features as possible. Let's look again at the loan approval model and these inputs: age, income, and applicant score. If we look at these hypothetical counterfactuals, we will say that, for example purposes, they all have the same calculated distance. We can see that despite having the same total distance, they do have different number of inputs changed. The sparsity property tells us that, in this case, we should favor the counterfactual which changed the least amount of inputs, which in this case is a single one. This also has an interpretability advantage. If we interpret counterfactuals in an n-dimensional space, even though all the counterfactuals might have the same distance from the original point, it is potentially simpler to interpret an input that changes only one feature than one that changes several. Formally, we can expand on the previous validity property, shown here, by adding a new term, and this term is a sparsity penalty, which increases with the number of features changed. Finally, let's look at the actionability property. Actionability can be defined as the ability to separate between mutable and immutable features. Although from a mathematical point of view the previous definitions might seem sufficient, from an explainability point of view we must account for features that shouldn't change. This can be for a variety of motivations, including legal and fairness reasons. And if we take a new example, where now gender and ethnicity are also inputs for our model, it is clear that we shouldn't change the original values of these inputs to produce a counterfactual. Instead of searching within the domain of all variables, we might wish to fix the values of these two to always remain the same as the original data. And this way, we can search by changing only the remaining inputs. Formally, we will define actionability by restricting the previous definition to a subset of attributes A, which are the mutable or actional attributes. Now that we've seen how to define a counterfactual, we go through on how to implement an actual counterfactual search. We've been talking about black box models and the formal definition of a counterfactual. A possible way of implementing a counterfactual search would be to express our definition in terms of the inputs and outputs we have and create a loss function that we will try to minimize numerically. Some common methods to perform this minimization are gradient-based search methods such as the Nelder-Mead algorithm. However, we'll be using a different approach. First of all, we use a constraint solver, namely OptaPlanner. OptaPlanner will allow us to abstract the core algorithm for a counterfactual in a way that is independent of the predictive model we've been using, and we can focus on expressing the search simply by defining a few quantities. We define the input, that is, what type of data our model consumes, along with our original values. The input domains, that is, where we want to restrict the search, and also what is our desired outcome. Under the hood, OptaPlanner will be querying the model and building a score for each potential counterfactual. And after a period of search, we will have the best counterfactual candidate. So we can see that the search and score definitions are abstracted away from us. We just need to define the data. But that's not all that is abstracted. Another advantage is that we could, for instance, use a different search meta-heuristic simply by configuring OptaPlanner to use a different one, and we wouldn't need to rewrite our search implementation. If we recall our formal definitions for the counterfactual properties, the validity, the actionability, and the sparsity, we can map them directly to components of an OptaPlanner score. Here we added a component called a confidence score, which will select counterfactuals for each the outcome prediction as a minimum confidence. The first three components will be what is called a hard score, that is, counterfactuals that do not meet these conditions will not be considered valid ones. And for the ones that pass that criteria, we will then rank them by the bottom two quantities, the soft score, that is the distance, and in the event of a similar score, we will favor the counterfactual which changes the least amount of features. Now that we defined our problem data and our score, the search will be performed by the highly optimized search implementations of OptaPlanner. We can use a variation of the previous example to illustrate a simplified search for counterfactuals in our feature space. Here we want to find which outcome we need to get a specific grade. We start by defining our search boundaries for the model's input, in this case the outcome, And these boundaries can be defined by someone using domain-specific knowledge, by general validation rules, extracted from the model's metadata, or in some cases from the actual training data. Next, we need to define our counterfactual desired outcome or goal. And as we've seen, this is not a minimum. We're after a specific grade. Our original data clearly did not meet the required grade and therefore was rejected. And for instance, the search can initiate by sampling a neighborhood centered on the random initial point. The samples inside this neighborhood can then be evaluated to see if they are valid counterfactual candidates. Some of them are not, and we discard them, and a new neighborhood is built centered on points that increase the counterfactual score. We can repeat the process until we have candidates that minimize all the previously seen score components. Since this is a minimal model, after a few iterations, we can see that we have a set of common counterfactual candidates. Each of them will have an associated score, which will allow us to rank them. As mentioned previously, this is a simplified illustration, and the actual search meta heuristics can be replaced, including writing our own custom search. And OptaPlanner also provides ways for testing and benchmarking different approaches to determine which ones are best suited for the problem at hand. So this concludes my introduction to counterfactuals. Thank you very much for your time, and I hope to see you soon.